forward. So, hey everybody, thanks for joining. I'm Finlay and I'm a co-founder of Safe Landing. So Safe Landing is for climate concerned aviation workers. We're really interested in looking at the impact of our sector and how we can rapidly reduce that in order to minimize, the impact to the environment, but also to safeguard jobs and careers in this sector going forwards. So you've got our website down there, safe-landing.org, and our email address as well, if you want to ask any questions, if you want to join our newsletter, or any of our Telegram groups where we work on stuff together. We've got kind of 4 demands as a group of our industry leaders, of our business leaders. The first is to be honest about the environmental impact of flying. The next is to be realistic about the limits of technology to solve this problem. And this is where the talk from Jayant comes in today, looking at electric aircraft, which is often proposed as one of the solutions to the CO2 problem of aviation. Then we want to be transparent about future regulations, what regulations are required to reduce emissions, and not lobby against those, crucially. Next, to have a plan that accounts for this and supports workers through any transition, because we think there needs to be a big transformation of the aviation sector and of the way we travel. Just want to also bring people's attention to a petition that we've got out now that's targeted at ICAO. Hopefully I've said that right, because I keep on saying it wrong. But yeah, it's the International Civil Aviation Organization. Now they're meeting, they've got a general assembly that's starting on Tuesday next week. And it's very much beating around the bush when it comes to actually dealing with the emissions from international aviation. There's an offsetting scheme that's very weak and very ineffective called CORSIA. And we think, from our perspective, aviation workers aren't given a look into this, and our sector, as we see it, is heading towards disaster. So we've got a petition that's asking ICAO to give us the controls when it comes to the future destiny of our industry, and perform an aviation workers climate assembly as soon as possible. So you can find the petition on our website, safe-landing.org/assembly, and there's a link to the petition in there, plus a promo video. So yeah, we've got Jayant in today. He's from the International Council on Clean Transport. And I'm going to stop sharing my screen. And he's come and presented to us before on hydrogen aircraft. I think your speciality is sort of zero emissions aircraft, isn't it? So a great person to get in and talk to us. The last talk was really informative, so I'm looking forward to this as well. Yeah, go for it, Jayant.
Yeah, thank you guys thank you, Finlay, for inviting me, and thank you all for tuning in. It's a Thursday evening. I don't know, not the most popular time for meetings or presentations. But today I'm going to be talking about electric aircraft. Previously, a few months ago, I presented on hydrogen aircraft at Safe Landing, but this is going to be focused on electric aircraft and the role that battery electric aircraft specifically can play in decarbonizing aviation. And spoiler alert, it's not a very big role. To start off with, I just want to introduce the International Council of ICCT, International Council on Clean Transportation, or the ICCT for short. We're sort of an independent nonprofit research organization, and we primarily advise governments worldwide how to reduce transport emissions using the best available science. And we focus on the research behind the policy decisions that we suggest. And I'm part of the aviation team. It's fairly small. It's only 3 people currently. But we've had a history of doing a couple of different projects. Mainly, we focused for a long time on airline ranking for emissions estimates, but since then have moved towards more predicting aviation emissions, tracking emissions, and from airports. More recently, we've been doing a lot of work on zero-emission aircraft and supersonics. We're trying to widen our expertise slate, I guess, to non-CO2 impacts in frequent flyer levies, which I think people at Safe Landing would probably be quite interested in. And there's a paper specifically about frequent flyer levy coming out next week, which I will share with Finlay as soon as that's out. And our future plans, this is mostly my plans. These are the projects that I'm hoping to undertake are in hydrogen infrastructure, urban air mobility, and sort of modeling modal shift from airplanes to trains wherever possible.
Just on that one, the hydrogen infrastructure, is that because that can mean quite a lot of things. Is it going to be the whole, like everything? Is it going to be mainly like looking at the fuel systems, or is it like actually for the aircraft we're going to need different airports and terminals and gates and all that sort of thing as well?
Yeah, so it's about the airport infrastructure, which will also, I think in this case, I haven't quite scoped it out yet, include hydrogen production on site and kind of what would be required to get that up and running, along with all the refueling stations and things like that. What it does do is sidestep hydrogen delivery. But our current research suggests that on-site production is probably the only way to, it would be the cheapest way to get hydrogen into an airplane.
Cool. Gonna need some nuclear reactors beside your airports then.
Or just like really large amounts of solar panels covering every inch of that runway side area.
Yeah.
But yeah, and so today I'll be presenting on electric aircraft, and the study focused on this particular question of what kind of impact electric aircraft could have on aviation emissions. Now, in passenger electric vehicles like cars, battery electric vehicles have become very popular and are growing rapidly. And so the idea is, like, people suggest often that electric aircraft could have the same impact on aviation, and that's kind of what we were trying to determine here. And also, like I said earlier, feel free to jump in with any questions. It's a few people, so it can be quite informal. But it is hard for me to figure out if you're like raising your hand or anything, so just unmute yourself and interrupt me. I don't mind. Now, having electric motors and battery-powered aircraft, it sort of opens up the design space to some very funky configurations you could do, like distributed propulsion along the entire wing and sort of benefit from some aerodynamic gains. You could have wingtip rotors to counteract the vortex formation. So there's like a lot you could do with electric airplanes if we wanted to not have to limit ourselves to a specific aircraft design. So we did a very simple analysis just based on like the electric range equation. So it does simplify a lot of the physics, but it also provides sort of guideposts for how much electric aviation could actually achieve. The aircraft parameters are sort of based on industry standards, and if people are interested, I have some backup slides on the exact details of how we filled in the electric range equation.
Yes, please.
Yeah. Well, so I will get to that towards the end. Just I'll give the details of the results first. On the most basic level, we modeled different pack levels, battery specific energies. We go all the way up to 1,000 watt-hours per kilo, but really 250 to 500 is kind of what you would expect, at least from lithium-ion batteries, in the near future. And by near future, I mean probably until 2040. I don't see huge gains in battery technology, and that's because lithium-ion, the chemistry itself is sort of limited on a pack level to not really exceed 500 watt-hours per kilo.
I think that's fair, considering that we've had a trend of about 5% increase for the last 100 years. It's a bit weird to think that it's going to be any different for the next 10 or 20 years. So yeah, I'd go along with that.
Yeah. And one of the things that we wanted to also include was the emissions of producing these batteries as well. And so one of the things we include in our emission factors is how much it takes to build a battery, and how often do you need to replace it in one of these aircraft, because when you have very short flights, you do a lot of duty cycles in a day. 3,000 duty cycles is approximately 8 flights a day for a year, or 4 flights a day for 2 years, just as a rule of thumb.
That is if you use the full cycle per flight, which isn't true. And did you also take into consideration recycling the battery packs? Because obviously the materials in there means, you know, you're going to recycle like 99% of the materials. You just need a bit of energy. So once you've got the battery packs, it's a totally different situation than mining them in the first place, right? Just like EVs on the road.
Yes. And so this is it. I don't think it actually. We don't include second life or recycling batteries because there really hasn't been a lot of that going on currently. And so we are not
73% of the batteries of the EV market in the Netherlands currently gets recycled.
Oh yeah. Okay. Well,
and the car manufacturers are actually by law obliged to set up the facilities to recycle the battery packs end of life. And like you said, there is also the second life of the battery packs because you need to pull them out much sooner in an aircraft, right?
And you can recycle 99% of the materials?
Yeah.
Wow. I'm learning something new. Well, I'm gonna have to look into that. But this
also look up Redwood Materials, which is JB Straubel's next venture after Tesla. So they're setting up a battery factory right next to the Gigafactory in Texas to recycle the battery packs, and there's several of that sort of ventures starting up around the world.
If you've got a good link for that, post it in the chat, Joseph. That'd be interesting.
Redwood Materials. Just Google it.
Okay.
Yeah. And so, okay, so with these sort of assumptions and using a electric range equation, what we get to, we model sort of 3 different sizes of aircraft: the 9-seater, 19-seater, and 90-seater. These are based on what is being currently sort of investigated in the industry. And we gave them cute little names: 9-volt, 19-volt, and 90-volt. And the ranges that we get for pack level battery specific energy for of 300 watt hours per kilo is they're sort of listed over here. So 211 kilometers, 100 kilometers, or 63 kilometers. These are comically small ranges, and you're not wrong to think that. And this is because a lot of the range actually gets eaten up in the reserve requirements for these aircraft, for operational requirements. And so what this addresses is about 0.01% of the commercial aviation market in terms of revenue passenger kilometers, and but a much higher percentage of departures, 2.6% of departures. That's because these are short flights that take off fairly often.
How do you get to 211 kilometers range on the Aviation Alice when they're giving like, I don't know, 800 or something kilometers
50.
range of the aircraft?
Because they're expecting a very, very light aircraft. Light, like, so, all right. The reason why we have such low ranges, is because, let me show you the reserve. If you have just a maximum cruise range using the electric aircraft, using some basic assumptions for the empty mass fraction and the final weight of the aircraft. The final weight of the aircraft that they say is 7,500 kilograms, or 7.5 tons. The maximum range you get is 426 kilometers. But then you include, this is a 30-minute loiter, 10-kilometer alternate, and a 5% contingency. And all of that sort of cuts down to a 211 kilometer range. What they expect, and the main difference between our model and what they have suggested in the past, is how much of their maximum takeoff mass is the operating empty mass of the aircraft. So this is just like the structure of the aircraft. They're expecting the structure of the aircraft to be in about 0.2. Like, that's where they want the empty mass fraction. These dots that you see here are all currently flying aircraft. So they're expecting a much lighter, they're claiming a much lighter operating empty weight than is really, honestly, feasibly possible. What we model is about a 15% reduction in the empty mass fraction from the state of the art. And we investigate like a 0% reduction to a 30% reduction.
So what you're saying is aviation Alice is lying massively.
It seems all the more challenging to reduce the empty mass fraction, as in general the battery mass actually is shifting into the operating empty mass, while for conventional aircraft, obviously, like all the fuel mass is getting burned, and that's not part of operating empty mass. So
yeah, so I also do define this operating empty mass without the battery. Battery I consider as a fuel, but I keep that constant in when we are doing the simulations. That doesn't change. Okay. Yeah. And so these are the ranges. On the x-axis, you have the specific energy of the battery. So that goes from 0 to 1,000. Y-axis is the operational cruise range. And these are the 9-volt, 19-volt, and the 90-volt. And the shaded area is sort of that range of empty mass fraction that I was talking about. So when you use like 250 watt-hour per kilo batteries, the operational cruise range, so minus all the reserves and everything, comes out to be about 250 kilometers at best if you have a 30% reduction in empty mass fraction compared to the state of the art. And that is a lot lower than what they're claiming. The 19-volt Heart Aerospace actually makes more reasonable claims, but I will come back to that in a second.
They've already cancelled that program. They're now doing a 13-seater hybrid aircraft anyway.
Yeah, and that's because so if you increase, coming back to this, if you increase the pack level battery density from 300 watt-hours per kilo to 500 watt-hours per kilo, your 90-volt is almost coming close to the 19-volt, and the 9-volt is sort of a feasible aircraft. But this is also like 500 watt-hours per kilo on a pack level. So that's doubling what is the current best-in-class battery in the Tesla. I think it's the Model 3, which is about 250 watt-hours per kilo.
Don't know. I still think there's something wrong with your calculations.
I mean, the paper has all the details of each parameter that we use. We have to make assumptions on L over D. We have to make assumptions on the takeoff mass, on the loiter speed, which is based on sort of a maximum lift coefficient value. And the empty mass fraction, which I just mentioned. And this is kind of what we come up with. But the details of the exact equations and the modeling.
Do you have the link to the paper?
Yes.
I can find it if you want to keep on going.
It was in the
chat.
Thank you.
Was also in the invite, I think.
Oh, okay. I must have missed that.
And so, we get some severely limited range because of these reserves. And you'll also notice that, yes, the ES-30 has come out instead of the ES-19, because when you try and do a 19-seat aircraft and keep it below the Part 23 weight limit, which is about 8,618 kilograms, so that you have fewer certification restrictions on there, then you have an aircraft that really can't do much. And that's why they shifted to a hybrid aircraft, which now they claim 200 kilometers only electric, 400 kilometers with hybrid electric, and 800 kilometers for if you reduce the passenger size to 25 passengers. The 25 passengers will probably just allow it to carry more jet fuel. So that will that's why that range bump is so large. And what we see, but sorry, it's not all doom and gloom. Electric aircraft are significantly more efficient than jet-fueled aircraft. Like these are energy efficiency ratios. So this is how efficient it is at cruise condition. The 90 would be 3 times as efficient as the same aircraft, but running on jet fuel, for 2.5 and 2.0 for the 19 and the 90 volt. This actually gets even more compounded if you're comparing these electric aircraft to an equivalent zero-emission jet-fueled aircraft, which is made, where the jet fuel is actually e-kerosene and is made with renewable electricity, which then has efficiency itself in production of about 50%. So only 50% of the energy that you put into producing e-kerosene you can get out of it. And so these energy efficiency ratios actually double when you compare it to a jet-fueled aircraft running on e-kerosene.
Jayant, sorry, like how do you define this energy efficiency ratio? I mean, if it's not too complex, otherwise I look at your paper, but.
It's purely just the energy required for cruise when you, and that is based on the aircraft flying, I think it was a 100-kilometer cruise segment, and I modeled this using Suave, which is a open source aircraft design tool, and these are the ratios that we come up with.
I mean, a simple way I'd think about it is like an electric motor is like 3 times as efficient as a jet engine, and that's roughly what you've got going on there.
Yeah, but the issue is that, you know, you end up with an aircraft that is much heavier. So, you know, you also consume more energy. So I'm surprised that you're, you know, 3 times more energy efficient. But is it per, like, do you divide per unit mass of the aircraft or per unit payload?
It is, no, so it is using the same, okay, yeah. It's not using the same payload in terms of, it's the same number of passengers. So it is the same passengers and luggage, but it isn't the same maximum takeoff mass. The jet fueled aircraft is lighter than the heavier electric aircraft.
Okay. I'm surprised by those numbers because we, in our studies, and we don't study, you know, like full electric aircraft, but already we have a, you know, kind of equivalent performance index. And, you know, we're quite worse than electric aircraft. Sorry, like electric aircraft are quite worse in terms of energy, you know, consumption per, you know, payload range traveled.
I find that quite surprising.
Anyway, I'll look into your paper.
It'd be good to compare because it's in like megajoules per passenger kilometer or per kilogram.
Yeah. It's megajoules per passenger kilometer that I'm comparing.
Okay.
In these.
So yeah, we can compare those from the two, and from Joseph's as well. Be interesting.
Yeah. And
I mean,
the reason why
our projections, we are at 67 watt hours per passenger kilometer, which is the same as the Dutch train, which is actually running on 100% renewable electricity. And it's just electric trains, whereas in the UK, we're like, I don't know, 38% of the railway in the UK is electric and the rest is still running on diesels. So, but yeah.
Yeah.
But here, if if the unit is megajoule per, no, there's no unit right here.
No, it's comparing, it's a ratio of the megajoules per RPK for electricity versus the jet fueled aircraft. So I think the reason is because turboprops on small aircraft are even worse than turboprops for bigger aircraft. The engine efficiencies are in almost like 25%. The overall efficiency of the electrical system in this case was, if I remember correctly, 0.82 if you multiply all the different efficiency values that we assumed. And so that's why
basically this figure energy you know, efficiency, it's, you know, if it's low, I mean, if the unit is megajoule per kilogram
RPK.
passengers, yeah, RPK, basically it's better if it's low, right? Okay, so
yes.
So here you're 3 times, you consume 3 times more energy actually. Is it that?
No. It's it's the way of you're comparing the megajoules per RPK of a 9-bolt versus a 9-seater commuter, which in our case was the Super King 250.
Okay.
And and when you compare those two, it basically the 9-bolt takes about a third of the energy to cover the same amount of distance with the same passenger count than the Super King 250.
Okay.
Yeah.
I mean, I think a big part of it also depends on what your lift to drag ratio is in the cruise. So, you know, for commercial aircraft at the moment, you also are burning a lot of inefficiently jet fuel on the ground, taxiing around and having the engines running before you even get to the runway. Then you know, you usually would actually fly faster than the maximum lift to drag ratio speed because jet engines are very expensive to maintain. So you try and cram as many flights in and go as fast as possible, pretty much, to get the most bang out of the buck in terms of your engine maintenance hours. Whereas with electric aircraft, you will probably be flying at close to maximum lift to drag speed because you want to minimize the energy consumption. So you're going to be flying slower.
Yeah, well, it's
So
that
I don't
thing
think
of
it's
like,
fair to look at the lift to drag ratios that a commercial, current commercial aircraft gets in the cruise, because that's not how you're going to operate an electric aircraft.
yeah, like when you fly faster with jet fuel, you burn the fuel off quicker and your mass becomes lower quicker. Whereas you don't have that incentive with batteries, do you? Because the mass
I
stays
don't
the same.
think that's much of an incentive. It's definitely pure about the cost of the maintenance of the jet engines. You know, like that you burn off a few more kilos in the cruise is going to make hardly any difference in your efficiency in the end, because you have to carry less fuel. It's you know, most of the time you're actually, half of the time almost on short flights, you're tanking fuel because it's cheaper in one airport than the other. So
yeah.
So I mean, I'm scanning through the paper, and I just noticed that, you know, you're going for a lift to drag ratio of 16, which is, yeah, it's not too bad. I was expecting worse, almost.
Yeah.
But yeah, I think.
Yeah, I was taking that from commercial cruise lift to drag ratios of not of the big aircraft, because those I think operate more on the 18, 19 range, but of smaller aircraft, smaller commuter aircraft, which are more lower.
I mean, the most produced aircraft ever, the Cessna 172, is only running at around 9-1. So lift to drag. And it has a much worse engine efficiency on top of that. So yeah, it's 16 isn't too bad, but it really does depend on what number you pick.
Yeah, and one of the side projects that I want to do is just make the electric aircraft calculator that I have into a little applet that I can embed onto the site, because they are very simple parameters that anyone can enter and get some sort of aircraft range, payload range capacity. But that'll hopefully, if I find time, I will do that eventually.
It is worth saying, like, if you have unless you have like a very unique configuration, alternative configuration like BLI or distributed propulsion, like if you're just looking at aircraft aerodynamics and all that sort of stuff, you can do that with jet fuel as well. So the comparison still holds to some extent.
You can't do distributed propulsion with a jet fuel as easily, but I wouldn't stay yourself blind on it, because the comparisons that I've seen with the data from NASA suggests that the lift to drag ratio in the cruise for a distributed propulsion aircraft is worse than a conventional one. So, you know, you can, it's great for short field takeoff and landing, but you're going to pay for it with efficiency in the cruise. So overall, actually, your range is going to reduce. It's really not that exciting.
That's why there have been so many interesting designs that have then been abandoned and everything.
Yeah, you see a lot of the distributed propulsion aircraft are going hybrid, and that's for a very good reason, because they're not that efficient. And it's basically the people that have done the Airbus, Vahana, and the Uber Elevate, and all the sort of spin-off eVTOL companies, and then have gone on to do that. They're just, you know, technical innovation for the sake of technical innovation without a real market for it.
Yeah, that is exactly right. And the one of the points about this energy efficiency ratio is that the reason why energy efficiency is super important is because if you say magically decarbonize all of aviation in 2050 and we're running electrofuels or hydrogen, regardless, the entire energy required by just the aviation sector would be the world's entire production of renewable energy in 2019. So you would need to add that entire capacity to already a grid decarbonization plan that is that needs to be aggressive to be able to decarbonize and make all of the electric things that we use more sustainable.
Yeah, I mean, you could also say that right now the emissions from the hydrogen industry are nearly as big as the aviation industry, like within a hair of each other. So if you're going to be making green hydrogen, then you should really be sticking that into the existing consumers and not looking for new markets for it. And it's just not very efficient, right?
Yeah, because there is a lot of just, yeah, hydrogen being powered by coal, or
96 or 98% of the world
yes.
hydrogen is made from fossil fuels. So it's it's
yeah.
I don't really have any words for it. But yet there are plenty of companies out there that are pursuing this hydrogen dream. But let's carry on with the slides and go deeper into the analysis, because I think we can talk about this for hours, and I'm just excited to see, you know, how you get to the numbers you get and the conclusions that you get.
I don't. I'm going to be completely honest. I don't have too many details of the exact modeling in this presentation itself, because I was tailoring it to be more general. But I'm happy to get on a call with you afterwards as well to talk about all the details of the modeling that we've done. One of the things that we finally want to see is also what are the carbon emissions of these electric aircraft. And to do this, we're comparing them across two different timelines, which is 2030 and 2050. 2030 assumes you have a 300 watt-hour per kilo pack level battery. 2050 assumes you have a 500 watt-hour per kilo battery pack. And the various different bars that you see are, so the brown bar is Jet A. These are the emissions of what you would, the aircraft flying on Jet A for a median stage length of about 76 kilometers, which is very short. That's why these are very inefficient aircraft. And then that is compared to if you run those electric aircraft on US electricity, which is even current US electricity, the decarbonized level, or what is stated in their policies to be the grid decarbonization by 2030, you still have less emissions than jet aircraft. So sorry, just to make this clear, this is the electric aircraft being powered by just grid electricity. So you're literally just plugging it into the wall, and you still have a more efficient and less carbon emissions, even with the grid mix that is projected for 2030. It's better if you take into account sort of the IEA's projection for what is a Paris Agreement compatible grid electricity mix. This is from their sustainable development scenario from their World Energy Outlook.
Do you want to hear the good news?
Yeah.
I don't think you have to worry about it too much, because it's actually cheaper to burn jet fuel than it is to take electricity from the grid in terms of energy per amount of money. because the grid electricity is so expensive compared to the cheap cost of jet fuel. So
Yeah.
no one in their right mind is going to do that, financially, commercially speaking.
Unless you tax
So
jet
companies
fuel
that
more.
are going to run electric aircraft are probably going to look to secure electricity that's generated at the airports,
Okay.
and have that off grid with battery storage at the airports, not taking it from the grid. It's just not going to happen commercially.
Finlay, your question is, I'm assuming, is it the same if Jet A gets taxed?
No, I was just just on the point about like how ridiculously cheap kerosene is at the moment. I think probably something we'd all agree on is that can't stay as it is for too much longer. So but you'd expect two things to come into play. One, an emissions pricing being applied to aviation fuel that accounts for maybe non-CO2 as well. It should be a lot higher than it is now. So that will make jet fuel more expensive. And then you'd expect the renewables mix on the grid to be a lot higher. So it's less volatile and dependent on gas prices, which should make the cost of electricity lower. So those are the things that are going to change, in my view.
Yeah, we know that in Europe there is increased taxes coming on jet fuel, and in the US and Canada as well. So it will start to get more expensive, jet fuel, for sure, and that will eventually balance things out. But hopefully, but still, you would still be crazy to use, as a commercial operator, to use electricity from the grid when it's 35 euro cents per kilowatt hour or whatever, when you can spend 5 or 6 euro cents per kilowatt hour if you just pay up front to have the infrastructure and it's yours at the airport.
Okay, that's
at which point it actually becomes a little bit cheaper than jet fuel.
Oh, wow.
This kind of goes back to a conversation we had at the start, which is around how many solar panels you can actually fit around an airport, particularly if it's in the middle of a large urban environment.
Not, I mean, luckily you can't do it with batteries anyway, flying across the pond. But it wouldn't work for that energy-wise, especially if you're just using all the big airports, the very few big airports. It wouldn't work. But we've done a study with Groningen Eelde Airport, and they had, at the peak in 2019, they had 250,000 passengers coming through that airport. And actually, if we flew all of those passengers with our battery electric aircraft, we would only be using about 20%, 20 to 25% of the electricity that gets generated there now with the 22 megawatt facility that they have there. And 22 megawatt solar facility is already small compared to some other airports that have put some serious solar panels down. So yeah, you can do a meaningful contribution with, and that's why I'm still pursuing this battery electric aircraft thing, because actually an aircraft does in its life more than 10 million kilometers, whereas your average car does 250,000 kilometers. So if you take into account the emissions that come along with actually manufacturing the vehicle, and how most people charge their electric cars versus just using solar electricity at the airports for the aircraft, not needing any infrastructure between the airports because you're just using the runway either end, so you don't need 400 kilometers worth of road. Actually, battery electric flying is the greenest mode of transport, bar none. So yes, it's not going to replace massive sections of current air travel, but it is going to play a big role in the future.
Yeah, that's actually one of the things that we want to compare our cross-mode battery electric vehicles, and the most direct comparison in aviation, which would be sort of urban air mobility aircraft, which are like 2 to 4 person aircraft jumping from one place to another. That's something we're just scoping up, and hopefully should be done by April or May next year.
Well, I think just for your context, like Joseph's aircraft is more like a fixed wing, which makes a big difference, right? Because eVTOL is like probably the
horrendously inefficient they are. It's really, I don't really see a market there either. This is just talking small, efficiently designed battery electric aircraft like the Aviation Alice, and even smaller and slower and more efficient than that.
Yeah.
Yeah, that's kind of where it's at, and none of the vertical takeoff and landing aircraft. That's just jokes.
Yeah. Another one folded today, actually, Whisk. So that's always a fun
I saw Kitty Hawk
thing
going.
Sorry, not Kitty, not Whisk, Kitty Hawk. Yeah.
Right. Okay. Yeah. Good.
Exactly. Yeah.
Yeah. And I can't actually believe that one of the serious investors that we were talking to commented on that he was surprised about it. And it's like, where's the market? Like, who's going to fly in an aircraft like that?
Yeah.
Like, nobody's qualified to fly in those things. There's no regulations for it. There's no real range.
Yeah, that's
what's your end user? What's your market? Like,
yeah, you get
12 years, and I don't know how many millions spent.
Yeah,
such a waste.
Yeah. Yes. Yes. Sorry, just gathering my thoughts again. So one of the things that you notice here is we also include the battery replacement emissions. This is, I say battery replacement, but it's the battery production that gets and number of batteries used per year, or per how many ever years, that gets included in this calculation. Regardless, electric aircraft, even if you are charging them on the grid, which I guess Joseph mentioned that wouldn't be economically feasible either, are less carbon intensive than jet fueled aircraft. This is sort of the happy part about electric aircraft. Back to the doom and gloom, and the question is, how far are we from batteries taking over different segments of the market? If you are focusing on sort of commuter, 19 passengers, 450 stage length, you need about 3 times the battery capacity that we have right now, 650 watt hours. But this, if you get to this level, then you have you can replace most turboprops with electric aircraft. When you're talking about regional aircraft, slightly bigger, slightly longer ranges, you need 1,500. Narrow bodies, you need 2,300 or 5,100. You need, basically, if you wanted to fly on a wide body, you would need batteries that are about 20 times as energy dense as they are currently. And so this sort of shows how much further we are from electric aviation taking over or helping decarbonize significant chunks of the aviation market.
And I think also there is a theoretical limit, in the energy density of lithium-ion battery. Yeah, I think it's around 2,600. So anyway, and that's
purely on like if you strip away everything about the battery, and just have the anode and cathode, and that's then you get that watt hour per kilo. Yeah.
Yeah, I mean, there's other solutions out there, but again, it's just nonsense. It's never going to happen.
Aluminum air batteries.
I definitely think that for long haul flight, we are going to have to use SAFs. Hydrogen doesn't make any sense either. We're going to have to use SAFs, and it's going to have to be a lot more expensive. It's going to have to be, you can use SAFs or nothing. You're only allowed to fly with SAFs, and it'll be at the price that it'll be, plus tax, emission tax, and all that sort of stuff on top. That's where we're going to hopefully end up with. And then you have battery electric for very short distance flights. But yeah, I mean, I'll let you carry on. But I mean, with our calculations, we do think that we could, by 2040, already go up to 1,000 kilometers with battery electric aircraft. And
carrying how big?
Doesn't matter.
Oh yeah, I guess it doesn't matter. It's a matter of the
battery mass
percentage. Yeah.
Well, I mean, considering that you've got 2 billion cars in the world, but only 30,000 commercial aircraft, like the number of vehicles that you need is kind of irrelevant, especially if considering you're only using a fraction of the airports right now that we already have. But coming back to the thing is, if you look at the emissions that aviation produces, then you see that there is quite a lot more flights happening of short distances than long distance flights. And that then results in somewhere between 20 and 33 or 34% of the aviation emissions if you can go up to 1,500 kilometers. I don't think we get to 1,500 kilometers by 2040, maybe 2050, probably not. But 2040, by 2040, we can definitely do 1,000 kilometers. So that is a lot more than the 0.1% of the, like in the paper.
But it is with far less significant passengers in the aircraft. And I know you're saying, well, you can just fly 100 times more aircraft, but you then say, well, the infrastructure to land those number of aircraft doesn't exist.
That's not true. I mean, right now I live in Southampton, and you know, Flybe used to do 97% of the movements there. That no longer exists. I used to fly 4 or 5 times, or I could fly 4 or 5 times from Southampton to Amsterdam. But Amsterdam isn't even where I'm going in the Netherlands. And now I can only fly once a day with KLM, or I can go to Heathrow or Gatwick to fly from there. But still, I fly to Schiphol. That's not where I'm going. You know, we're using NASA regional air mobility paper says as well. You know, we're using like 10% of the airports that we have globally, and the rest we hardly use. They're also struggling financially. So I don't think that and I think again, these numbers in terms of numbers of passengers, you can make the aircraft much bigger if you wanted to. It is really, I don't think the number of passengers makes a difference to the efficiency of the aircraft. It's the range that the distance is the killer here. So if you took these calculations here and you put the stage length at the same for all of them, you'd see that actually wide body aircraft still have a lift to drag ratio of around 19 or 20 to 1, just like the short distance ones do. So that's the metric.
If you have, yeah, I mean, if you have the same stage length out of all of these, the wide body aircraft would actually require less than the commuter aircraft, because when you have bigger aircraft, you can have less of the structure, like the empty mass fraction can be lower, and you can fit more batteries for the same.
Yeah, exactly. So it's not limited to just small aircraft.
Yeah, but then you're also carrying a 400 passengers, 400 kilometers, which in terms of
it doesn't make any sense now. Yeah. But the situation where we now have like 30,000 commercial aircraft flying and 2 billion cars, which most of the time are parked up, is messed up. And I think what we are going to see, and even NATS realizes this, that by 2040 we're going to add like 10,000 aircraft a year to the global fleet. We're going to have many more aircraft flying to small airports and connecting those together than we've ever seen before.
I'll be interested to hear what the air traffic manager, thinks about that. Like,
yeah. So I mean, it's an interesting conversation, because obviously we often talk about the capacity limits being the amount of tarmac that we've got available, which is obviously an issue. But it's not just that, it's through the TMAs as well. And I don't think that the targets that we're putting out as an industry completely make sense, because we are, the industry is saying that it will have a set amount of growth, and it's saying it will have a set amount of operational improvements as well. So looking at, forget what sort of aircraft you're flying, any sort of aircraft at the moment, where there's certain studies that say we can have 6%, 8%, even 10% improvement from operational efficiencies. So no holding, continuous climbs, continuous descents, optimum cruise levels, that sort of thing. And the more aircraft you put in the mix, the less that's possible. And I don't think that that's, it may be appreciated, but it's not spoken about. It just doesn't add up.
This is like people saying that you can't reuse a rocket. You can't land the rocket back on its arse, and see what's happening with SpaceX. Like, the technology is there to do it. It's just that management and technological progress in air traffic control is still in the Stone Ages.
Yeah,
It's ridiculous.
It's a very, very slow process. I completely agree. It's a frustratingly slow process at times, and we're working with decades-old technology. And I don't really see that changing. Certainly within NATS, our programs to, well, probably be careful what I say, but the programs that we've got to replace equipment are just pushed back and pushed back.
Yeah, but that's because there isn't a need to do it. And that's the thing. Once there is the need to sort it out, because there is a big change, a shift, and you can't cope, that's when suddenly things start happening a lot quicker. And it will be the bottleneck at one point. It will slow things down, but it isn't an unsolvable problem.
Bottleneck in a lot of ways in 2019. I mean, the capacity crunch of 2018, 2019 talked about across Europe a lot. And the driver was all about capacity at the expense of environment. It's very kind of fickle how it can seem to shift as well. But ultimately, we don't have enough new technologies coming in that are going to make the difference that we need for the predicted growth. It will just result in more inefficiency. There's a recent snapshot come out from Eurocontrol. It was looking at continuous descent operations, and actually it was saying that since 2019, the inefficiencies around Heathrow and Gatwick are a lot less. And it's like, well, it's obvious why, because there've been less aircraft, so we can make them more efficient. We don't have as much holding. We have more continuous descent operations, but the aim is not to consider that. It's being ignored largely at the moment. So I don't, it's all very well that air traffic might talk the talk about providing the capacity, but it's a very, very difficult thing to do. Everything is very difficult to implement new stuff because of safety across the whole of the industry, as we're all aware. And certainly on an air traffic side, it can make new things really difficult to come in.
Yeah, and single European skies is a great example of that. It's been in the works for so long and has been promised for so long, but has not seen the light of day in all the research that has gone into it, to the point where everyone working on the project now, when I hear presentations about it, everyone complains about how it's just not getting implemented. And that's a problem.
Yeah, it's a really difficult one. So I work on the Single European Skies ATM research project, and the view of a joined up Single European Sky just isn't realistic in the near term at all. What it is a number of smaller implementations of improvements in quite a piecemeal way, which can bring some benefits, of course. It has done. There have been benefits from it, and there are benefits in the pipeline, but they're not at the scale that we'd like to see. Yeah.
Cool. So just with an eye on the time, because we're almost at 1:30, how much do you want to kind of just finish off your presentation, and we'll see how much time we've got left?
Yeah, I mean, the rest of the presentation is nothing. These are just sort of recap slides. I was going into an overview of what the zero emission technologies are, whether it's hydrogen fuel cell or hydrogen combustion aircraft, and kind of the markets that they would take up. So this is the overall aviation emissions attributed to different distances and capacities of aircraft. What you'll see is that narrow bodies, if you add these up, come up to about 50%. Wide body, but the single biggest chunk is the wide body long haul, or wide bodies in general are about 50 or 40% of all aviation emissions. Battery electrics can take up this little part, and if Joseph is also suggesting 1,500 kilometers, you could come up to here, but everything else would require either hydrogen combustion or SAFs, and those are both incredibly energy inefficient to produce. And so there's a lot of challenges with decarbonizing aviation, and like we talked about before, flying will likely get more expensive, and demand management through pricing increases will be a really important tool. And ideally, we want to be shifting as many people as we can to trains.
Yeah, so
and
this is
where the
the thing
infrastructure is
where I'm a little
available.
bit like I think for short distances, yeah, sure, take the train maybe. Long distances, it's not really an option to take the train, and in fact, sometimes actually, I mean, right now, if I take my petrol or diesel car and I drive to the Netherlands on my own, I would actually produce more emissions than if I just go on the plane.
But your baseline here isn't a very good one, because driving a single passenger occupancy car is like horrendously inefficient.
I know, but
itself,
that's the option I have, because that's the car I have. And right now in the world we're making, I don't know how many million electric cars, but we have 2 billion cars to replace, and it's going to take another 30, 40 years before we replace the fleet.
I do get into this conversation. I debated the CEO of Loganair, which is the biggest domestic airline in the UK, right? And he was kind of saying, but if we don't fly, then everyone takes cars, and I'm there. I think we need to be very crystal clear on this. We need a radical reduction in passenger miles, period. And that includes.
Yeah, and that's what I'm saying is, like, don't just take the car or the train. Consider whether or not you actually need to travel.
Yep. And then when you do travel, you want to maximize your capacity factor, right? So if
take the family and go for a week, not just on your own for a day.
Yeah. So if you're looking like in the UK, London to Glasgow, comparing any aircraft to a single occupancy car isn't great, because you should be comparing it to high capacity factor coach or train is what we should be aiming for, right? And I think that's the interesting. I think my kind of summary of that graph that Jayant just presented is like the electric aircraft can't make much of a bite into the existing air transport network that exists. But what's kind of more interesting is at those smaller scales, the competition with other modes of transport and what the relative energy efficiencies are. And then I think for me, it comes down to like the cost of electricity for different things should probably be subsidized in different ways to benefit more efficient things. And I probably see a mix of electric aircraft and electric coaches and electric trains, because we can't build infrastructure for trains everywhere. But yeah, I just see that Robert's got his hand up, so I'm keen to bring you in, because you've not had a chance yet. So what's your question?
Hey, Robert.
Yeah, thanks. Good morning. So my question, Jayant, is about the news in the past week, which was that Hart Aerospace cancelled their 19-seat plane and announced a hybrid 30-seat plane. Now, you would agree, I guess, that earlier model was never ever going to fly. I got a lot of media attention, and now the new one's getting media attention, and everyone's forgotten about the old one that they were so enthusiastic about. So there's this very dangerous ecosystem between the venture capitalists funding things that are never going to work and the media jumping on them. So yeah, I guess I'm concerned about that aspect of the whole transition that we're just starting now. What's your view on that?
Yeah, no, I wouldn't say I was surprised by it, but I'm surprised that they went for a 30-seat hybrid. Mostly because when the papers that I've read about hybrid electric powertrains is usually that it's extremely heavy, and that's a penalty that becomes prohibitive. And this is something I think I forget who on this call was. Vincent. He does research on this, so he might be able to talk more about it. But I mean, like, these numbers on the face, they seem reasonable in terms of technological feasibility. Whether it makes economic or environmental sense, I'm not 100% sure about.
The new model, the hybrid model.
Mm-hmm.
Well, the idea is that you basically don't touch the jet fuel, right, unless you need to do a diversion mission. So you would essentially be flying in fully electric until you had an issue and we're like, actually, we need to divert, we need that extra range capacity. And that then means you don't carry as much dead weight batteries most of the time. But I don't think have they made it clear what sort of hybrid electric it is, whether it's like a jet engine that's driving a generator to.
Yeah, it's two generators in the back that are supposedly range extenders, so they should only come on when you've depleted your batteries, so to say, which means that they've got a power rating that actually allows them to carry on flying when that happens. But then they're still giving also the option of doing 400 or 800 kilometer hybrid electric flights. So operators will probably end up flying more than the 200 kilometers with this aircraft, and therefore putting some emissions out. And they say that it's like 50% reduced emissions by operating this aircraft compared to conventional aircraft. That's kind of how they're marketing it.
Yeah, I mean, it does look more plausible on the engineering side, but then there are other startups that have even more ridiculous proposals that they're claiming that they're going to implement. So it looks like some kind of rort or fraud to me, but it could just be that this is just a bit of fluff that happens in modern economies and we don't need to worry about it, see what happens. Or is it like
I think there's also the operators to blame here, because basically operators that have placed orders or are looking at placing orders from Heart Aerospace, the more seats on bums they can stick in those aircraft, the lower the operating costs are for them. So the more it fits in with what the public wants, which is low cost tickets for the operator to be competitive in the market. So that's why they didn't want to have less than 20 passengers, and 19 passengers is cheaper to certify an aircraft because CS23, but they already worked out they couldn't stay within the weight limit for CS23. So then let's go for more passengers. We're going to be CS25 anyway, and we make the operator happier. Mm-hmm. So it's not just investors, but it's also the operators that are forcing, in this case, an aircraft designer, an aircraft manufacturer, to make these sort of commercial decisions. And
I think the reason why it gets so much media attention is it's every so often there's a new airline that partners or orders or puts in orders for these aircraft that don't exist yet, and that's why it keeps flooding the news channels. Most of those MOUs aren't binding either.
Thank God that the Boom supersonic one aren't binding, because that aircraft consumes like 6 or 7 times more fuel than a non-supersonic aircraft. So it's just nuts. If you're gonna run that off on SAF, your energy consumption is
just on the safe landing perspective on this. I mean, in some ways you could say, I mean, just going back kind of 5 years, I was quite a big advocate for my company Rolls-Royce working on electric stuff, and even if it was eVTOL, because I was kind of like, that's where the investor money's going. It looks really shiny and fancy. Investors are giving billions to it, and it's a really good place to rapidly innovate on smaller, lighter electrical systems that can be then applied to more reasonable, probably fixed wing aircraft. But I think over the last 5 years, I've got more and more disillusioned with that, because you can see just the insane amount of money that's going into these aircraft that really don't make any environmental sense, yet are labeled as kind of pioneering sustainable aviation. And this is kind of true for both the supersonics and the eVTOLs. And I kind of see like an eVTOL like a electric SUV of the sky, right? Like it's really not what we need to do when it comes to sustainability. We need to making things small, like
isn't the good news here that Rolls-Royce pulled out of being the engine manufacturer for Boom Supersonic, and now all the other manufacturers are also saying no, thank you very much.
Yeah, I can.
So
They did
it.
just today hire the ex chief technology officer of Rolls-Royce, though, to give them some credibility. And I've had a bit of a debate with him on LinkedIn today. But yeah, just like finish that point. I just think it's a great shame, really. There is so much investor money, and it's not, in kind of our opinion, going in the right places, because there's so much work to be done to transform the aviation sector. You know, maybe the future is much more small local airports, much lower payload and speed and smaller aircraft flying a more distributed network. Maybe there's some role for hydrogen as well. I don't think anywhere near as much as we're currently flying, and we will need to fly a lot slower to really conserve energy, even more so there. But that is so much engineering work, so much infrastructure design change, and we needed to have been getting on with it 20 years ago. So it's so frustrating just that some of the best and brightest minds when it comes to aerospace engineering are working on these projects, right? I think that's kind of the big loss. It's not just that, you know, ultimately some of these investors are going to get misled and they're going to lose their money. I care a bit less about that, but more just that some of the most, you know, intelligent people I know are working on these concepts, and they're kind of dead ends when it comes to sustainability.
No, I totally agree.
100%, yeah.
So yeah, I'm
Yeah.
kind of we've gone. Is there kind of probably got time for one question, but we're a little bit over because we've had such an intense debate. But I think it's been really informative. Has anyone got any sort of burning question they're keen to ask or add to that before we finish?
I see one question in the chat from Dennis,
yeah.
and about policy. And I don't think, in terms of electric aircraft, I'm not 100% sure what policy other than taxing Jet A would make a direct impact. The policies that I have been involved with right now is Refuel EU, which is the EU's mandate for using a certain blend of SAF in all European airports. And I think that's the first regulation of its kind, first regulation to make aviation sustainable in the world, I think, or more sustainable. And so that is very interesting. It's extremely, it's quite aggressive in its targets as well. One of the amendments from the parliament actually raises the SAF mandate to about 80% by 2050. So using 80% blends in jet fuel by 2050, which is still not 100% sustainable, but still is extremely aggressive given the timelines that we have been on in SAF production.
Yeah, I think it's kind of like subsidizing the wrong thing as well. You know, like if what we're saying, there's some aircraft that are clearly more sustainable, and the kind of concern is all the money's flowing to the ones that use like maximum megajoules per passenger kilometer. And it feels to me like there should be government incentives towards R&T for stuff that's going to deliver minimum megajoules per passenger kilometer, right?
Yeah.
But so, and I think we'll need to not just think about jet fuel tax, but also be thinking about how do we tax different electricity users and making sure that we're kind of clamping down on the high energy consumption uses, even if that's 100% green energy. We should not be subsidizing electricity going towards places that are just burning that energy away.
Yeah.
Cool. So yeah, thanks very much, everyone. It sounds like there might be some stuff that some of you could send to Jayant and vice versa. He's going to send it back to me, and I can share that on our mailing list and on our social medias and stuff. Just a flag that we've got this petition to ICAO that I mentioned at the start. Not everyone was there, but I've just put that in the chat, a link to our website. ICAO are running their assembly next week, and we want to get as many signatures as possible to say, let's do a workers' assembly and look at some of the topics like this, and let workers have a say about the future of our industry. And I'm running a talk on workers' assemblies, if you're interested in that, this time next week as well. So you'll see that advertised on our social medias. So yeah, thanks everyone for joining, and for all the good questions and detailed discussion. I think given even we had like a relatively small amount of people, there's quite a lot of expertise in the virtual room, so that's been really good. I hope you.
Yeah, I learned quite a lot, so that was fantastic. Thanks for organizing, Finlay.
Awesome. Right. Have a good evening or morning wherever you guys are. And yeah, catch you all soon. See you
Thank you
later.
very much. Bye-bye.
Bye.